Okay, so in this particular lecture, we are going to talk about closed sets. Okay, so before talking about closed sets, let us first discuss a few theorems related to open sets. So, a theorem. So, every open set in R, whenever I write R with respect to its usual metric. Okay? So, every open set in R is union of a countable family of mutually disjoint open intervals. Mutually disjoint or pairwise disjoint, whatever. So to understand this theorem, let us first discuss an example, a very simple example we will understand. So let us choose an open set in R. Let's say we have this open set 1, 3. Okay. If I take this countable family of intervals, say 1, 2 and 2, 3. Okay. Let this be G1 and let this be G2. So this is indeed a very countable family, very evident from this. And the union will give you this set, right? And they are mutually disjoint, and each of them is an open interval. Okay, so I hope this theorem is clear. So let us first discuss the proof of this theorem. Okay? Before discussing the proof of this theorem, let us first discuss one more important thing. That is, suppose you choose an open set in R. Okay, so let G, a non-empty set G, is contained in R, is an open set. Okay. Why do we choose G to be non-empty? Because if G is empty, then this theorem is very trivial. So let G be a non-empty set in R which is open. Okay. And we take two elements from G. Okay. Let us take two elements from G such that there is a relation between them. Which implies there exists an open interval. There exists an open interval I in G such that X and Y belongs to I. Okay. So what we do is that we choose an arbitrary non-empty open set from R, and and when we take two elements from G, there exists relation between them, or we define a relation between them such that there exists an open interval I in G, and X and Y both are contained in I. Okay. Now you can obviously check it on your own that this relation is an equivalence relation. This relation is an equivalence relation. And if this relation is an equivalence relation, then this relation, partitions this whole set into equivalence classes, right? This relation partitions this whole set into equivalence classes. What I try to say is that if you take this equivalence class, let's say xi, and you take their union, let's say I is from let's say I belongs to capital capital I be an indexing set, and all these xi's belongs to G. Okay, where all these xi's such that I belongs to capital I belongs to G. Okay, or rather let me write it like this. Where xi belongs to G for all I belongs to capital I. Okay, this equals G. This is what I try to say. And each of these xi's are mutually disjoint. Okay, if you take xi intersection xj, okay, then either this is empty, and if this is non-empty, then xi equals xj. Okay, Okay, clear? Clear. So one part of the proof is basically done from here itself. Okay. What we need to do is that now we need to check whether each of these equivalence classes are intervals or not, and there exists a countable family of such equivalence classes. Okay. This will give us the proof. This will give us the proof. Okay. So let us do so. So 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 to prove this xi when all I belongs to indexing set I is an interval. Is an interval. How to prove that this is an interval? So if we take two elements which belong to this interval, every element in between them must also belong to this interval. So let us take two elements belong to this interval. So let alpha beta belong to xi such that let us take alpha less than beta. Okay. Let us take alpha less than beta. Okay. Okay. Now if alpha beta belongs to xi, so that basically means that alpha and beta are related to each other. Alpha and beta are related to, and if alpha beta are related to each other, then that implies there exists an open interval I in G. I is open interval. Okay, such that alpha and beta both belong to I. Right, right. Now if so happens, if there exists an open interval such that alpha beta belongs to I, and alpha beta, so that what does that basically mean? That basically means this closed interval alpha beta, this is basically contained in I, right? This is basically contained in I, because alpha beta they belong to I, and every element between alpha and beta belongs to I. So this closed interval alpha beta belongs to I. Right, right. Is it clear? Now suppose we take any arbitrary element from between alpha and beta. So suppose there exists r such that alpha less than r less than beta. Okay, r is any arbitrary element between alpha and beta. Now if so, then that implies r is belonging to this interval. R belongs to I. And if so happens, so if R belongs to I, then we can obviously say that R is related to alpha or beta. So R is related to alpha. So R is related to alpha. And if R is related to alpha, that means R is contained in this equivalence class Xi, right? So that basically implies Xi is an interval. Okay? Specifically an open interval. Specifically an open interval. Okay? We are not talking about any sort of containment at this moment, so Xi is an arbitrarily an open interval. Okay, clear? Now, how to check whether these sets of equivalence classes are countable families? Okay. Now, what we can do is that so since we are talking about R, that is a set of reals, so we can form these equivalence classes, or rather, we can say that each of these equivalence classes contain at least one rational number, right? Each of these equivalence classes contains at least one rational number, right? So the the family of these equivalence classes, each containing one rational number, we can create a set of rationals from them, extracting one rational number from each of these equivalence classes. Okay. Okay. That will give us a subset of rationals, and a subset of rationals is countable. Since we're taking exactly one rational number from each of these equivalence classes, and that set is countable, the set of the equivalent classes is also countable. Okay. So what I try to say is that now there exists at least one one rational number in each of these equivalence classes. Okay. Extracting exactly one rational number from each of the classes forms a subset of rationals which is indeed countable, which is indeed countable, which implies set of these equivalence classes, that is the family we are talking about. So these equivalence classes is countable. Okay. So we have thus proved the theorem. Is it clear? So is the theorem clear? Okay. This lecture is going to be a short one. Okay. So now let us move on. Now we will be talking about what we call the neighborhood of a point. Okay. Neighborhood of a point, or rather neighborhood of a set. Let's say neighborhood of a set. Neighborhood of a set. Neighborhood of a set basically indicates the neighborhood of every point on that set. Okay. So pretty much trivial to understand what's neighborhood of a point. So let XD be a metric space. Let XD be a metric space, and we take two sets from them, from X, such that A is contained in B. So B is said to be a neighborhood of A if there exists an open set S contained in B such that A is contained in S. Okay. Okay. So this definition is given in Siemens book. Yeah. Okay. If you study Rudin's book, you will see that B is said to be a neighborhood of A if B is open. Okay. In Rudin's book, you will find this definition. B is said to be a neighborhood of A if B is open. Okay. Because if B is itself an open set, so we can choose S to be B. As simple as that. Okay. Okay. Or we can arbitrarily say that A is contained in the interior of B. Whatever definition you may like. Clear? Now let us discuss one more thing. Now we have already discussed how can we induce a metric from one given metric, right? We already discussed is that suppose XD is a metric space. Let Y be a non-empty subset of X. Okay. So Y dy is also a metric space. Is also a metric space where dy is a metric induced by D. Basically, if we restrict this function D in such a way that the domain becomes this set Y, as simple as that, that gives you a metric space Y dy, right? Or that gives you this metric dy. Is it clear? As simple as that. Nothing very complex. So this definition we recalled because we need to discuss one thing. The thing is a theorem. I am not going to prove this theorem, but I will give you the exact hints you require to prove this. So the theorem says that A is open in Y, where A is contained in Y and Y is contained in X, provided X and Y are metric spaces. Provided X and Y are metric spaces. If and only if there exists an open set G in X such that A can be written as an intersection of G and okay, this is the theorem. A is said to be open in Y if there exists an open set G in X such that A can be represented as the intersection of that open set in X and Y. Okay, so I'm giving this to you as an exercise. Okay, but I'm giving you the hint you require. The hint is something like this. So suppose you have A contained in Y contained in X, and you choose an element from Y. Okay, let A belong to Y, which automatically implies A belongs to X as well, and let R be a positive number. Okay. Now what is this open ball A R with respect to Y? Okay, so open ball AR with respect to Y is basically we are trying to form this open ball using but the centers are basically points from Y. Okay, but the centers are basically points from Y. So every point in Y is indeed a point in X. That is what I am trying to say. Okay, so this is the set of all those points in Y such that distance between A and Y is less than R. And if we form an open ball with the same center but with respect to X distance, that is we are considering this point not to be a point of Y but more generalizingly a point of X. Okay. So this is the set of all those elements from the metric space X such that distance of AX is less than R. Okay, is it clear? Now can from here we say that this open ball UYAR is nothing but this open ball UXAR intersection Y, right? Because this open ball restricting the elements to only those points in Y is what this intersection gives. That is indeed this open ball. So using this thing you can obviously understand how to move on with this proof. Is it clear? Is it clear? Okay. Now we move on to the definition of what we call a closure point. Closure point. So let XD be a metric space. Let XD be a metric space. Let A be a set from X. Okay. So an element from X is said to be a closure point of A if for all positive numbers open ball centered at X and radius R intersection A is non-empty. Okay, then X is said to be a closure point of A. Does this definition directly implies that this X will will trivially be an element from A, right? Right. Now from this definition we get one more definition which is called the closure of A. This is called the closure of A. So closure of A is the set of all those points such that they are closure points. Okay, they are closure points for all R greater than 0. Okay. So from this statement and from this statement, can we say that A is contained in its closure? Obviously, right? Obviously, right? Yeah. Okay. So let us quickly move on to our next definition, which is the definition of limit points. Limit points. So what is a limit point? So limit point is simply is simply that point. If you form a ball with that at the center, then it has a non-empty intersection with A except itself. Okay. Let me write it down. So X is a metric space as declared earlier. So X belongs to X is a limit point of A if ball with center at X and radius R intersection A minus X, okay, is non-empty for all positive numbers R. Okay, that is, there exists at least one element other than X in A. Okay. Okay. So from this statement, can we say that if X is a closure point, and X does not belong to A, then X is a limit point? Very trivial, right? Very trivial, right? If we form a set of all limit points, then we call that set a derived set. Okay, we call that set a derived set. So derived set is the set of all limit points of A. Okay, and from the definition of limit point and the definition of closure point, we can obviously say that a closure is nothing but the union of A and its limit points, because every closure point is an element of A. Every closure point is an element of A, and every limit point is also a closure point, right? Right? Clear? So this is the thing. Right. This got it? And if I just say what a closed set means, let's say what a closed set means. Closed set A in a metric space XT is a closed set if and only if it equals its closure. It equals its closure. Okay? That is the definition of a closure point. Sorry, that is the definition of a closed set. Okay. Before ending today's lecture, let me discuss one more thing. That okay, I'm giving this as a theorem and I am providing the necessary steps you require. Okay, that is the theorem says let A be a set from this metric space XT. A is closed if and only if X minus A is open. Okay, so I'm leaving this proof as an exercise, but I'm giving the necessary hint. Okay. Okay. So suppose X belongs to capital X is not a closure point of A. So that implies X belongs to X minus A closure, because X not being a closure point of A means X lies outside the A closure. This is what it means, right? And if so what does this basically mean? So if X is outside A closure, that basically means that there exists some positive radius R such that a ball with center at X and radius R intersection A is empty, right? Is empty. So what does this mean? So this means UXR is completely contained in X minus A, And what does this mean? This means that X belongs to X minus A interior, right? X belongs to X minus A interior. So have we automatically proved that X belongs to X minus A closure implies X belongs to X minus A interior, or rather which is called the exterior of A? And if you carefully notice, all these steps are symmetric. That is, all these steps are equivalent steps, right? Sorry, biconditional steps, if and only if steps. Okay. So what does this mean? That X minus A closure is equals to X minus A interior. Okay. So you can use this to prove this thing. Okay. So let this lecture be up to this one, guys. In the next lecture, we will be moving on to some more details about closed sets, further discussing about Cantor sets, and moving on with our lectures. Okay. So meet you guys in the next lecture.